Thank you very much, everybody, for being here in another session of our QRC seminar. Today, we have Professor Eric Lutz from the University of Stuttgart here with us remotely. It's a pleasure to have you here. I've known Eric for already quite some few years. So he's now a chaired professor of theoretical physics at the University of Stuttgart. And before that, he was professor of theoretical physics at the University of Erlangen-Nuremberg. And then he was also group leader at the Dahlem Center for Complex Quantum Systems in FU Berlin. That's actually when I met him. He's got already several grants, Emmy Noether, several postdoctoral fellowships, and he's a worldwide authority in quantum thermodynamics. In fact, we were discussing many ideas. So, well, who's an authority, like international authority? To me, at least, I've learned lots of things about quantum thermodynamics from him. He's also a guy that's interested in quantum information questions. And over the years, he has done several contributions to the field. It's really a pleasure to have you here, Eric. And please go ahead with your talk. Thank you very much. Okay.
Thanks for inviting me. And I'll start by sharing my screen. So I'll assume that you see my screens from here. And please feel free to interrupt me if you want to.
We see it. We see your screen and your mouse, and we hear you well.
Perfect. So I would like to tell you a little story about how to use dynamic Bayesian networks to derive non-equilibrium generalizations of the second law of thermodynamics known as fluctuation theorems. So I'm going to assume that you don't know anything about the topic. And the outline of the talk is in front of you. It's very simple. I'm going to tell you a few words about these generalizations of the second law known as fluctuation theorems, how to get them without Bayesian networks, and what are the shortcomings. And then in the second part of the talk, I'll move to fluctuation theorems with dynamic Bayesian networks. I'll try to convince you that this approach is much, much, much better. But before starting with the talk, before starting with non-equilibrium thermodynamics, I would like, as a teaser, just say a few words about joint probabilities in quantum mechanics. So that's something that you know very well. Let's assume that we have a quantum system in an initial eigenstate J1, and we want to get the probability to know the probability to find the same quantum system in a new eigenstate J2. And what we teach students is this transition probability is simply given by this expression. Right? It's the modulus squared of the matrix elements of U, where U is the time evolution operator. If we are now interested in the joint probability of measuring J1A and J2, we simply consider this product, meaning the initial the probability of having the system in eigenstate J1 at the initial time times this transition probability. And this probability is very often used, or theoretically and experimentally determined, theoretically and experimentally by applying projective measurements to our system. So the question now is, and I'm not going to answer it immediately, but only throughout the talk, is how should we generalize this joint probability if the system now does not initially start in an energy, in an eigenstate, but in an arbitrary quantum state, for instance, a superposition of eigenstates. So how can we theoretically and possibly experimentally generalize the idea of a joint probability, something that we know very well here, to states which are superpositions of states. And that's not something that happens very rarely in quantum mechanics. I mean, superposed states are all over the place. So that's the teaser. I'm not going to answer the question. You can think about it during the talk, and I come back to that question at some point during the talk. Since this is a talk about non-equilibrium physics, I thought it might be a good idea just to have one slide, short introduction to main ideas of non-equilibrium physics, non-equilibrium statistical mechanics. And I'm going to start with something which is elementary, the definition of the entropy production. So what we teach students is that for an equilibrium transformation, meaning when the system starts in an equilibrium state and stays in an equilibrium state at all times, then the change of entropy of the system, delta S, is simply given by the heat exchanged with the bath divided by the temperature of the bath. So that's Clausius. Delta S is simply Q over T, but this is only true as long as the system is close to or at equilibrium. Now, if we drive the system fast so that it cannot remain close to equilibrium at all times, we have to modify this equation by adding a quantity capital sigma, which is by definition the non-equilibrium entropy production. And in small system, this quantity is going to be random. It's a stochastic quantity because the system is going to be subjected to thermal fluctuations and to quantum fluctuations. So I'm going to talk about the thermodynamic properties of small systems. So this quantity is stochastic, that's what I just told you. And the question is, how can we characterize these fluctuations? I mean, they do not really exist for macroscopic systems. So we want to characterize them. And what people realized some 30 years ago is that there's a universal form, the universal equation satisfied by this P, which is the probability distribution of the entropy production. And it's a simple symmetry relation that tells us that P of sigma divided by P of minus sigma is e to the sigma. So if I turn this around, we see that the probability of having a negative entropy production is the same as having a positive entropy production, but it's exponentially suppressed. So you might remember that for macroscopic systems, fluctuations are negligible, entropy production is always positive. But if the system is small, the entropy production can be positive or negative, but the negative events, negative entropy events are exponentially smaller than the other ones. That's the reason we don't see them in big systems. So this is known as a detailed fluctuation theorem. If you now integrate over sigma, we simply get what people call an integrated fluctuation theorem. It's just the same. It tells us quite universally that e to the minus sigma is always equal to 1. And this equality implies this well-known non-inequality, namely that the entropy production is always positive on average. So actually, it's useful to see this from the other side. This is the standard second law of thermodynamics. Entropy production is positive on average. And if you go to the left, you get a generalization of that. E to the minus sigma is equal to 1. So this is seen as a generalization of the second law of thermodynamics for small classical and quantum system. And people were very excited, and are still excited, by these fluctuation theorems because they are valid arbitrarily far from equilibrium. Not just close to equilibrium, the linear response, but arbitrarily far. You can drive them as quickly as you want, and this characterizes the fluctuations of the entropy. So these are fluctuation terms. Two cases are important. The first one is mechanical driving. So you take your system and take your Hamiltonian and apply a potential which depends on time. You apply some external force, and then the entropy production has some very simple form. It's the work that you do on the system minus the free energy difference divided by kBT. This is the beta here. So this is mechanical driving, and the fluctuation theorem holds. That's Jarzynski, 1997. Another situation of interest is if you have two systems at two different temperatures. In that case, the entropy production is simply the heat exchange between the two systems times the difference of the two inverse temperatures. That's thermal driving. Again, Jarzynski and a collaborator, Wojciech, a few years later. So these two fluctuation theorems for mechanical and thermal driving has been extensively studied for classical systems for about 20, 30 years. And they're very useful theoretically and experimentally because they allow you to do thermodynamics of small systems when there are fluctuations. So you could do thermodynamics of colloids, of enzymes, and even of molecular motors. And that's the reason why people in biology are very interested in these fluctuation theorems. And you can see some example here to beads attached to a DNA molecule, and you simply pull them, and you can, for instance, get the fringe difference, the equilibrium fringe difference between initial and final state by doing some non-equilibrium work. So that's the reason why these things are interesting and important. What do we do at the quantum level? So at the quantum level, people apply what is now known as a two-point measurement scheme, meaning you apply a projective energy measurement at the beginning, you do something in between, and then you do a projective energy measurement at the end. And that's in that way you get the probability distribution of the heat or the work. So I start, again, you perform a first projective energy measurement, get some energy eigenvalue EM naught. You do something in between, heat exchange, mechanical driving, and at the end, you perform another energy measurement, get another energy eigenvalue. The difference between these two is the heat or the work. And since these quantities are stochastic, you average over all the initial values and you average over all the final values. And in this way, you get the distribution of either work or heat. And for those who pay attention, what you realize here, what you see here is nothing but the joint probability I mentioned on my very first slide. So this approach, this so-called two-point measurement approach, has been very successful because it allows you to capture the discrete nature of the energy spectrum, which you clearly see here. At the same time, because you have some transition probabilities here, you get all the non-equilibrium quantum dynamics. The plot at the bottom is just an illustration of that. These are the transition probabilities for a quartic harmonic oscillator, so that x to the 4. The black line is the quantum result. You see nice oscillations. The red one is the classical limit. And there's a clear difference, right? The classical one is not able to reproduce all these interference effects, which you see in the quantum regime. And now people were interested in the last 15 years or so how to measure experimentally this probability. Yeah.
Eric, one question. Can you go back
Please.
to the previous slide?
Sure.
So the quantum nature of the system is reflected, let's say, both by the spectrum of the Hamiltonian and also the transition probability, this P of NM, which kind of involves the evolution under the unitary operator, right?
Yes. So this U allows for
any type of dynamics.
Linear superposition of states, right?
Mm-hmm. All right. Okay. Thank you.
And that's the reason why you have these interference effects, these oscillations down there, in the quantum case.
Okay. Great. Thanks.
So far, so good?
Yes. Thanks.
So people were very much interested in measuring these probability distributions experimentally. And I'm just flashing here 1, 2, 3 PRLs where people have come up with schemes to actually go to the lab and determine them, not to calculate them, but to measure them. So all these approaches work very well. They're slightly different, but they're equivalent. And this has led to the experimental investigation of these fluctuation terms in the lab. So the very first one, it's an experiment done in NMR. That's the group of Roberto Serra in Brazil. And they were the first one to verify a mechanical fluctuation term the system they considered was this carbon atom, this hydrogen atom here, it's a qubit. You drive it by applying some external radio frequency field in a forward and a backward way. And at the end of the day, what you do is you have a two-level system and you modulate the level spacing, the gap, and reducing it in the forward process and increasing it back in the reverse process. And by doing that, you actually induce transitions between these 4 different levels. 4 different levels means that you have here 4 different contributions to the probability distribution of the work. The first thing to notice here is you have 4 values only. So it's a quantum system. You have a discrete work distribution, which is not the case in a quantum system. And then you take the ratio of the forward and backward, take the log, and you get a very nice straight line. So this is the first experimental verification of such a fluctuation term, p to the sigma divided by p to the minus sigma is e to the sigma in a quantum system. The second experimental verification was done in an ion trap, in a trapped ion system, in a group in China. They used a harmonic oscillator, and the work was done by simply shifting it. So it's a shifted harmonic oscillator. They did 2 different kinds of drivings, a slow one, adiabatic, a fast one, here an instantaneous push, an instantaneous shift. And they were able to measure the work distribution for these different driving speeds from 5 microseconds to 25. And sorry for that. And you can see you have, again, discrete peaks and work distribution, and you can use that to verify fluctuation terms. A very last experiment before I continue, this was mechanical driving for a qubit and for harmonic oscillator. And of course, you can do, using, for instance, this NMR with 2 spins, you can do a heat exchange fluctuation term, thermal driving. You can see again the distribution, the discrete distribution of heat now, 3 discrete peaks. You take the ratio, take the log, and you get these straight lines. It's again an experimental verification of a quantum fluctuation term, this time for heat exchange. So this works very well, theoretically and experimentally. So you might wonder, what is the problem? The problem is that everything is determined by performing.
Eric, can I ask you something else?
Sure.
So the way you define the work distribution in the initial slides also takes into account the initial probability distribution of the state n.
Sure.
Right.
So this is sure.
But so I mean, I think that all the interest in dynamics is contained in the conditional probability distribution, right? Or why do you make it explicit the dependence on the initial distribution of states? Wouldn't you be happy with the conditional probability distribution from n to, or I don't know?
I come to that in a second, but typically this Pn is a thermal distribution because you want to do thermodynamics. You have a thermal state at the beginning, so that's the reason. But people always average over the initial thermal state.
I see. Okay,
that's the reason why this P is here.
Okay.
But talking about conditional things, I mean, give me just a few seconds.
Okay, great. So thank you. Yeah,
you're welcome. So this two-point measurement approach, as the name indicates, is projective in nature. So you perform projective measurements. And this is clearly a problem if you have an initial state which has some quantum coherences or quantum correlations, meaning as soon as you have off-diagonal matrix elements in the energy basis, you perform a projective measurement and all these off-diagonal matrix elements are gone, all the quantumness is gone. So I think everyone would agree with me that quantum coherences and quantum correlations are central features of quantum mechanics. So we throw them out by performing projective measurements, and all these fluctuation relations I just presented can be considered as not being fully quantum. There's something missing, right? The quantumness of the initial state, or the final state for that matter. And this brings me to the second part of my talk. What do we do to include quantum correlations, quantum coherences, quantum correlations? What do we do with off-diagonal matrix elements in the energy basis? And we'll try to show you that we can capture them by forgetting about this projective measurement approach, but by replacing them instead by what people call Bayesian networks. And I'm going to define what this is. To make things concrete, I'm going to focus on one very specific situation. It can be generalized, it has been generalized to other cases. So I'm going to consider system A, thermal, system B, thermal. I'm going to present some experimental results at the end of the talk. So this is going to be one qubit, qubit A, another qubit, qubit B. The total time evolution of the bipartite system is unitary, they're isolated, and the only process that can take place is the heat exchange, Q, between these two systems. And I'm going to assume now that, system A is a thermal state, system B is a thermal state, but now there are some initial correlations. So this guy here is going to create off-diagonal matrix elements. In order to follow the discussion later on, I'm going to introduce two different bases. The first one is I simply diagonalize the joint state, or AB. So S is my global basis. And then I trace over A over B. I have the two reduced bases, A and B. So that's the notation. Global base is S. The local bases are obtained by diagonalizing the reduced density matrices, A and B. That's all I'm going to need. And I'm not going to become very technical in the following. That's just that's the only math I'm going to need. And now we're facing two different problems. A mathematical problem and a physical problem, and the two are of course related, but the first mathematical problem is that the global state S is not diagonal in the energy basis anymore. This is obvious because there are initial correlations between the two systems, but this means at the same time that these bases, the global and the local one, are not mutually orthogonal anymore. They are not compatible anymore, and this is going to make a problem. So the physical problems related to that is that the local bases, which I obtain by tracing over the other one, either A or B, they do not contain all the information about the systems, which is clear. I trace over all the rest, so they don't contain the entire information. And this is bad because if you want to do the thermodynamics, heat, work, entropy production, they're only determined via these local variables. So you throw things out, and with what remains, the local variables, you try to do thermodynamics, and it's clear that you miss something. You miss the quantumness. And the big question is, how do you include the missing part? Right? You want to do heat and work, you want to do thermodynamics defined via local variables, and you want to know something about the off-diagonal matrix elements that you typically throw out. The answer is, one possible answer, the one I'm advocating here, is we can use so-called dynamic Bayesian networks. So I'm just telling you what they are in an elementary fashion, and then I'm going to repeat it one more time slightly differently, hoping that you will get the gist of that. So I'm going to consider two time evolutions. The first one, I'm going to call that the global time evolution. That's simply the evolution in the global basis. It's the time evolution of the global state. But then what I'm really interested in, what I need to do the thermodynamics, is the time evolution of the local basis, small a for qubit A, small b for qubit B at different instances of times. And the quantity I'm always and I will calculate is what Leandro just suggested, the connection between these two. When we have some conditional, I'm going to calculate or introduce conditional probabilities. I want to have the probability of having state AI and BI given the global state S at time Ti. And this conditional probability is simply obtained by applying Born's rule at the end of the day. So there's nothing mysterious. Having that, I can define two things. The first is a so-called condition trajectory. So it's simply the time evolution of all my states as a function of time given the global state. So this is my trajectory. If I want to use the word trajectory, it's a trajectory condition on the global state. And I can calculate all the probabilities or the probability of that trajectory by multiplying all the conditional probabilities. So that's the initial. You can read the formula. I just multiply all the conditional probabilities, and in such a way, I get the probability of that condition trajectory. I can do that for a forward trajectory by starting here and moving to the right, but I can start on the right and move to the left, and I get the reverse trajectory, which is defined in exactly the same way. Having that, I can now sum over all the global states, and I get a joint probability. It's simply the probability of having A naught, B naught at time t, t naught. The same for all the times ending with AN, BN at time Tn. And this is the joint probability that I introduced on my very first slide. So that's the teaser. I just defined or just constructed this joint probability, Born's rule. This is true for any time, any number of times. So I'm going to make things simple and just consider two times, the initial time and some final time and some process in between. And that's this joint probability for two times, time t and time t prime. Now, if I don't have any initial correlations between my qubits, the bases are compatible. They're the same, actually. The global basis is the same as the local one. And then my joint probability is nothing but what I introduced on my first slide. That's the standard two projective measurement. The initial probability times the transition probability. But this is a special case of that. So this quantity actually contains all the information I was missing at the beginning. Everything, all the information about the off-diagonal matrix element. So this guy here knows everything about quantum correlations and quantum coherence. This one does not. So that's the usefulness of a dynamic Bayesian network.
So Eric,
yeah.
In the previous slide, so here this example, the other one, the next one. So in this example with two times, so S is the initial time. So you have S and S of t.
Yeah.
Right?
Or it should have been t prime. Sorry about that. This t prime here. Sorry.
Oh, okay.
So I start at t is equal to t0, and that's t is equal to t prime.
I see. All right. So you sum overall the initial states according to the initial Hamiltonian eigenbasis, right?
Exactly. So this only knows something about local quantities because I summed over all the global ones, but I did it in such a way that I did not throw the off-diagonal matrix, the information about the off-diagonal matrix elements out of the window.
All right.
It's a mathematic. Yeah. So I might have lost a few people because I don't know. I don't, that's the only math I have in the entire talk, but I cannot really skip it. That's the definition of the Bayesian network. So I'm going to repeat the same thing without any math, just using words. So what is a Bayesian network? One possible definition is to say it's a formalism to analyze conditional dependencies in a set of time-dependent random variables. It's very general. You have quantities that are connected, they depend on time, and you want to analyze how they depend on each other conditionally. So the relationship between these dynamic variables is simply specified by using conditional probabilities and Bayes rule, hence the name, Bayesian network. And it doesn't have to be a quantum variable, this should be clear. So Bayesian networks have been used since the 50s, in the 60s, extensively actually in statistics, in engineering, in computer science, and they were used to model time series in any probabilistic models you can think of. It can be anything. And repeat, the only thing you really need is a set of variables that are intercorrelated, they interact with each other, and they change in time. And that's it. And then you want to investigate how the change of one influences the other one. The mathematical framework for that, one mathematical framework for that is dynamic Bayesian networks. That's the only thing. So they've been used to predict future events, do inference about hidden variables or decision making or whatever. And Leandro, you had another question.
Yeah, so there is this graphical visualization of Bayesian networks given by directed acyclic graphs, DAGs.
Yeah.
I think
this
is what you were showing 2 slides before. No, 2 slides before you were showing that, right? So
it's
here,
a simplified version of it, yeah.
Okay, okay. But yeah, so you may think that this ST1, ST2 are like random variables, and then you have the causal dependencies, and then the local variables are like the children of the S nodes, right? Can I
exactly
think it like that? Okay,
it's exactly what it is.
Okay,
it's exactly what it is.
All right. Thanks. Yeah. Okay.
You're welcome. So for people who have not heard about Bayesian networks before, but maybe have heard about hidden Markov models or Kalman filters, these two are special cases of dynamic Bayesian networks. So it's very, very generic, maybe too generic to grasp them at the very beginning, but it's a nice tool a powerful tool to investigate in any classical or quantum system, this relationship between time-dependent variables. That's it. I'm more or less at the middle of my talk, and it's always good to make a small joke in the middle, I think. And I could not resist. And when I looked at early papers on hidden Markov models, you always find one quite well cited by Stratonovich, published in the Journal Theory of Probability and Applications, 1960. And the only reason why I show you this paper is because on the first page, you have some editorial notes, and I find it so great that I cannot resist. I have to read it. So part of the exposition of the problems with continuous time is not wholly convincing, but in view of the great interest in the problems raised, the paper is published in the form in which it was submitted by the author. And when I read that, and when I read what you get from referee reports nowadays, I think there's a lot that has been lost, right? So it's not completely convincing, but still, you trust the author and you publish it nevertheless. Take it for what it is, right? But yeah. So the editor was kind of, okay, fine. And he was right? Because it's not only convincing, but the treatment was correct. So now let me come back to physics, right? I started by saying a few words about fluctuation theorems, about extensions of the second law of thermodynamics. Then I moved to Bayesian networks, and now let me move back to non-equilibrium physics. And I told you how to determine a probability P of a given path, gamma, using my dynamic Bayesian network. I could do the same for a reverse process, and I'll just take the ratio of these two probabilities for the system that I introduced a few slides back. Qubit A, temperature TA, qubit B, temperature TB. Heat flows between the two, but they are initially correlated, and that's the fluctuation theorem where you get. So you recognize the Jarzynski-Wojcik result, that the entropy production in the classical case, the difference in inverse temperature times the heat, And all the quantities in red, or in color pink and red, are the new quantum contributions. So this is a classical contribution, the two projective measurement result. That's what you do if you project at the beginning, at the end. This I naught here is the initial stochastic quantum mutual information, meaning if you take the average over everything, this I average is the quantum mutual information. That's the one at the end. And then you have some sigma A and sigma E, B. So these are quantum relative, stochastic quantum relative entropies for system A and system B. So they simply describe the entropy production in qubit A and qubit B. That's the physics behind that. But the important point is you have 4 new terms that do not appear if you apply the projective measurement approach. They only come up if you do it using the dynamic Bayesian network. I told you at the very beginning, you have 2 different kinds of fluctuation theorems, detailed ones and integrated ones. You take the average over it and you get e to the sigma minus sigma is equal to 1. Again, you recognize the entropy production for the 2 projective measurement approach, and these 4 terms are what they have all the quantum properties, quantum correlations, quantum coherence. And I'm going to come back to that in a second. But the interesting thing is that not only the sum of these contributions satisfy fluctuation theorem, but all of them individually. So not just delta beta times Q, the entropy production satisfies the fluctuation relations, but the initial mutual information, the final mutual information, and the different entropy productions in the local systems. So these are all quantum, they are all quantum generalization of the second of thermodynamics for small quantum systems. This was theory, but there are also experimental results showing that it works actually. And I'm going to use the last few minutes I have to tell you something about how to use these dynamic Bayesian networks in experiments. So this is an experiment that was done in the group of Roberto Serra in São Paulo, Brazil. It's also an NMR setup with 2 different spins. So the molecules that they have used in the experiment is chloroform. That's the one they used in the old times to put people asleep before surgery. It's a simple molecule, actually. And the 2 atoms of interest are these 2. Hydrogen, so that's qubit A. Carbon, that's qubit B. Everything is in this superconductive coil. And they used to do NMR experiments. And then you prepare them in a thermal state, temperature T8, temperature TB, and then you engineer some thermal contact between the 2 so that heat energy can actually flow from one to the other. So this is the initial state used in the experiment. As you can see, it's very simple. So this is rho A is the reduced density operator of qubit A. It's a thermal state at some given temperature, so it's a Gibbs state. Rho B is another Gibbs state at a different temperature. And this term here is the correlation. This guy is going to create, or this contribution, these correlations, this interaction term is going to create off-diagonal matrix elements in the energy basis. And it's very simple. It's a combination of 0 and 1. But now, without this term, when you have the tensor product of 2 thermal states, it's diagonal in the energy basis, and this one is going to create off-diagonal matrix elements. These are the off-diagonal entries destroyed by projective measurements. And I'm going to now show you some experimental results. That's the measured probability distribution of heat. So we have qubit A, qubit B, 2 different experiments, one, no correlations in between. So that's the uncorrelated on the right-hand side. And what you see on the left-hand side is what happens if they are initially correlated. So uncorrelated means alpha is equal to 0. Correlated alpha is different from 0. And you clearly see that there's a difference. So you see 2 graphs on top, 2 graphs at the bottom. So this is for the forward process, and this for the reverse process. And there are 3 different values, minus QA, minus the change of the heat of the energy of qubit A, plus QA and 0. So again, it's a quantum system. We have a probability distribution of heat with 3 different contributions, 3 delta peaks. And just by comparing this line with this line, we see that the presence of correlations changes something. And you see what changes by looking at the detailed fluctuation relation for the heat exchange between the two. Correlated, these are the purple dots, uncorrelated, these green triangles. Without correlations, we expect if you take the log of P and P reverse, you expect a straight line, which is verified experimentally without correlations. If you have initially correlations, the fluctuation theorem is modified. So if the new contribution to the fluctuation theorem, and this leads to the fact that now you don't have a straight line. These three dots, the purple ones, are not on one line anymore. And this change in the slope is actually directly related to the presence of quantum correlations at the beginning. To make that clearly, let's move to the individual fluctuation theorem. So by looking at all the contributions, that's the quantum mutual information. Let's start here. That's the quantum mutual information at the beginning. That's the classical mutual information at the beginning. That's the relative entropy of coherence, the quantum contributions, and that's the entropy production in system A, and the same at the final one. And this sigma is just the sum of everything. And as you can see, all of these e to the minus something, they are all equal to 1 on average, meaning that we have some second law of thermodynamics for the local entropy productions in the 2 qubits. That's not surprising, but we also have second law of thermodynamics for the relative entropy of coherence at the beginning and at the end. We have a second law of thermodynamics for classical correlations and for quantum correlations, for everything. So which is kind of interesting because you can use thermodynamics now for everything, for quantum correlations, quantum coherences, and not too surprising, quantum entropy production. What does that mean? What this means concretely, this is an application now. I can analyze the energetic cost of creating quantum coherence of quantum correlations. How I do that? I just start with my 2 qubits. Initially, no correlations between the two. So I0 is equal to 0, only I1 exists. So that's the mutual information. The C is the relative entropy of coherence. And by using my fluctuation theorem, without initial coherence, I have these Clausius-like inequalities showing that the time derivative of the end of the mutual information, so the creation of correlations, is upper bounded by heat, by energy change, times delta beta, which is the change, which is the difference of inverse temperature. So this is a Clausius-like inequality. It's a second law of thermodynamics for the creation of quantum correlations. And then we can do the same for the creation of quantum correlations. This C1 is simply the relative entropy of coherence, the time derivative of it. And again, this is also upper bounded by the energy change, by the heat flow, times the change, by times the difference of inverse temperatures. And that's the experiment. The upper bound in both cases, these are the purple squares, and you nicely see that all the other ones are below that. So it's a nice first experimental verification of these Clausius-like inequalities for the creation. It tells you how much energy you need, actually, what the energy cost of creation of quantum coherence and quantum correlation is. The other thing which is interesting to note here is that I1 dot and C1 dot, they almost agree during the entire experiment, meaning that you only create quantum correlations and quantum coherences, but no classical correlations. There's absolutely no contributions from that. This would be the difference between the two. No classical correlations created, only quantum correlations and quantum coherences. And this brings me actually already to the end of my talk. I'll try to finish on time. And I told you many different things, and I guess you can safely forget everything except these 2 points, which I think are the most important ones. So quantum fluctuation theorems, generalizations of the second law of thermodynamics, can be obtained theoretically and experimentally by using this very powerful dynamic Bayesian network approach, which has a complicated name, but is very simple. to use in practice. You just need Bound's rule at the end of the day, conditional probabilities. And this allows you to go beyond what has been done so far, the last 15, 20 years, because you can fully include the effect of quantum correlations at the beginning, at the end of a process, and in between. You can do the same for quantum coherences at the beginning, at the end, and in between, and they can be fully included. And that's the reason why I would like to call this generalization of the second law of thermodynamics, this fluctuation relations, as fully quantum. We can now do the full non-equilibrium thermodynamics of a correlated, interacting quantum antibody system. And I think that's the reason why they are important for the future. And if you want to know more about the theory or about the experiment, I would like to refer you to these two PIs down here at the bottom. And that's it. Thanks for staying. Thanks for listening.
Eric, thank you very much for the very interesting talk, and congratulations on the results. Also, thank you for making it concise and short. This has been a very good exposition. I have a couple of questions, but I would give room if there are other people in the audience with questions. If not, I can proceed. Actually, sorry, I think that Andreas is on the chat. Can you Nel, can you click on the chat to see his question, please? I think that he was asking something. Let me see. And in the chat icon, there was one value.
There was one value which was lower in the figure with the purple. Why?
Oh, okay. This is a very technical thing. I don't know.
You mean here? Because it's true data, because it's a true experiment, and not everything is perfectly controlled. Things fluctuate. I mean, the main reason, that's the true reason, actually. And in all these NMR experiments, the fields are not exactly homogeneous as they should be. So there is the higher bounds, as you can see. So it's a true experiment, and it's only the short answer. The experiment is not perfect, and that's the reason why it's slightly below. But it's borderline within the error bars. It's not a perfect experiment. It's a real experiment. That's the answer.
So okay, I have a couple of questions. So when you do in this experiment by the Sarah group,
but Leandro, if you allow me, just one remark, on that. I mean, the error bars is 1 sigma. Right? That's how they calculate error bars in experiments. It's typically, I mean, you put a Gaussian, take 1 sigma. 1 sigma, that's 2/3, 67% of the points should be within error bars. So if any experimentalists show you in the future experimental plots like these, where everything matches within error bars, there's something fishy, right? When 1/3 of the points should be outside the error bars. I mean, it's 1 sigma, meaning 67%, 1/3, and this is it, right? It's only one. You could cheat and show 2 sigma, but this is a 1 sigma error bar, so not everything can be within the error bars. Right? Just as a side remark, 1 sigma, 67%.
Right. Yeah.
And I stop for the remark. Yeah.
So one question about the state creation in this molecule that you are showing. So in the experiment by Serra, so when you go back to the molecule, so essentially there, okay, so you choose to prepare the state of this hydrogen atom and the carbon atom in this initial Gibbs states at some given temperature, inverse temperature, right?
Yeah.
And then you choose where to put correlations or not. And so
between these two guys.
And so these, like, they control it like up to detail. Like, can they? This is easy for them experimentally. Can you make a remark on the experimental state preparation here? Like,
it's the preparation is challenging. I mean, it's a 2-qubit experiment. They need a huge number of pulses to create that. They need a huge stability to keep them. It's a challenging experiment. It's not done one afternoon after a coffee. No, it's a challenging experiment.
I see. And then the Hamiltonian that you use when you say these are Gibbs states. So this refers to the local Hamiltonian, the local energy Hamiltonian of each atom, right?
Yes, that's a Gibbs state. I mean, it's a qubit. So Gibbs states are, you can always define the Gibbs state for a qubit. It's a 2-level system, but it's the local energy basis, yes.
I see. Okay. And then the last question, okay, is more conceptual. So you describe Bayesian networks. So you didn't actually show how you use them in your scheme, right? Like
I did
I mean,
without.
you mentioned that the interesting thing for you are these conditional probability distributions, and I assume that you decompose that as a kind of like Bayesian network, and you try to see who are the conditional distributions there, but you didn't show the actual Bayesian inference thing that you
No,
do, right? Or
no, it's. I mean, I thought it's supposed to be a colloquium, not a technical talk, and I was very
it is. It is.
worried
No,
by
no, you
showing
did
these
super well.
slides already.
It's me kind of trying
Oh,
to dig deeper.
but I can tell you how to do it, right? So the P of gamma is defined here. So it's just the probability of this S times all the conditional probabilities at all the times. So
right.
let's stop at 2 times. You have this and this. You define the same for the reverse time, for the reverse process. And then you take the ratio and you see all the quantities which appear here. You need to, you take the ratio and you identify all the contributions. I mean, it's not as trivial as I just said, you need to do, but it's just identifying all the contributions.
But then in the experiment, I mean, you sorry, if I get it correct. So you go to the experiment and you determine, you kind of determine who are these conditional probability distributions in your, okay, this you do experimentally.
You want to know the experiment.
Yeah.
You want a theory or experiment?
Experiment.
Experiment. So the experiment, we made up our life simple. They heavily used process tomography.
Oh,
so they reconstructed all the density matrices all the times, and they actually calculated it. And but we have another scheme which does not rely on tomography, and that's something that you are going to be very much interested in because we use copies.
You use what?
And copies, different copies, and you used copies in the past yourself. So we can determine, we have a non-tomographic scheme to determine all these quantities by using a quantum system, and it's got 2 copies if you have 2 times. Okay. And then you can perform, or you can reconstruct all the quantities without having to do full process tomography, which scales exponentially with the number of states, which I mean, it's okay if you have only 2 qubits. If you have more, it doesn't work. But we have something which is non-tomographic, and we use different copies of the system of interest.
Okay.
And I can tell you more next time we meet it.
Yeah.
If you're interested. Or I can send you the paper.
Sorry, one question here. Yeah.
Yes, thank you very much for the interesting talk. Why, probably a stupid question, why there is a very huge number of quantum fluctuation theorems? Because, for example, I know about quantum fluctuation theorem using the resource theory. What is probably, how to say, what do you think? What is the the best quantum fluctuation theorem, or they play other roles in different applications?
I can give you the answer. I mean, I'm going to give you 2 answers. The first one is, I'm going to digress slightly, but I find it interesting. I teach electrodynamics this semester. And for that reason, I decided to read the history of electrodynamics. And it's a very nice it's a very nice, there are many books, but one which is very nice. But never mind. And what I realized is that nowadays, when we think about electrodynamics, we think about Maxwell's equations. But if you look at the 1860s, 1870s, there were many competing theories how to do electrodynamics. I mean, Clausius had one, Neumann had one, Helmholtz had one. So you had 4, 5, 6 different theories of electrodynamics. And at the end of the day, the best one survived. And this is Maxwell's theory. In quantum thermodynamics at the moment, it's just the same. no one knows what the best method really is, right? So people were using two projective measurements extensively. You have other people using resource theories. You have other people using full counting statistics. You have other people using quasi-probabilities. So there are 1, 2, 4, and 4, 5 different approaches. Each one has advantages, each one has disadvantages, and the best one, the unified formalism, ask me in 20 years.
Okay.
I don't know.
Okay. Thank
I
you.
don't know yet. I mean, and it's still work in progress, right? I mean, the very first experimental verification of a quantum fluctuation theorem was 2014. That's 8 years ago, and it's one boring qubit, right? And do the same for an interacting quantum antibody system. No one is able to tell you how to do that. So the true established formalism, I don't know, but I hope to know.
Might there be even more fundamental underlying results behind all these huge fluctuation theorems?
Yeah, it might be. It might be, and no one knows. When the resource theories the resource theories that you mentioned, they have big advantages. They're very abstract, don't rely on any details of the system. At the same time, it's very hard to connect them to experiments because they don't rely on any details of the system, right? So it's my honest short answer is it's too early. It's too early. People are trying things. I like very much this Bayesian network because it does everything I expect it to do. But again, if you look at the date, we published the first theory 2020. That's 2 years ago. The experiment was October last year, and we're still exploring different things. I'm okay, if you want my honest opinion, but I'm completely biased. This one is more powerful than all the others, especially two projective measurement approaches, resource theories. That's the one I'm going to defend and promote in the future. I might be wrong. I'm not going to be the next Maxwell of quantum thermodynamics. It might not be the one, but so far, as far as I'm concerned, it's the best one.
Okay. Thank you. Thank you very much.
Thanks for the question.
Great. Thank you very much. This is great because I was going to ask you a little bit about the perspective of this research program, but you've already answered.
At the moment, it does many things that the others are not able to do. Okay. Until we realize there's a big flaw somewhere and it's not what I expected to do, but let's see.
Great. Do we have any other question here? Okay, great. If not, then I would like to thank you again for the nice talk, congratulate you for the nice results, and hopefully see you soon at some point here physically. Visit us
I would love to.
Abu Dhabi, and hopefully retake discussions also about collaborations. Thank you so much.
I'll come back to you after the break. Thanks for having me, and hope to see you everyone someday in
thank you
live
again,
again.
Eric. So we thank the speaker again.